This is an image of the Milky Way galaxy, or how we imagine it to look. Across our night sky, there is a very faint band of stars that we call the Milky Way. It is the galaxy that our sun, alongside several billion other suns, exists together. And we can see what our galaxy looks like by looking out from our galaxy at other nearby galaxies. You need to imagine these almost like cities separated by a bit of countryside. These galaxies are separated with empty space in between. Now, our sun in the Milky Way galaxy is about 2/3 of the way between the centre of the galaxy and the edge. Our galaxy itself is a spiral galaxy. It has these great spiral arms in which new stars are being born in great number. What I want to draw to your attention is along these spiral arms you can see these pink sections. These pink sections are where stars are being born. It is a nebula. Now all of these stars are rotating around the central supermassive black hole that we find in the centre. And the closer you are to the centre, the faster you rotate. That's why the whole spiral structure has twisted itself up. But now I want you to imagine that maybe you are a clump of gas over here, and you have an extended size. But that is going to affect what happens to you as you move around the centre of the Milky Way. If you have an extended size, then the inward edge of your nebula is going to be trying to rotate around faster than the outward edge of your nebula. And so your nebula is going to try and have a very slight rotation as a result of its extended size, and this rotation is really important. Now imagine this. Imagine this is your nebula spread out across space. If one side of it, being closer to the centre of the Milky Way, is going to rotate slightly compared to the other side, then the whole nebula gains a small amount of rotation. But that's not the only thing the nebula is going to do. You see, all of this is attracted to all of this because of gravity. Here we don't just have a thin, tenuous gas, we have probably 300 stars worth of gas, all spread over just a few light years of space. Now what of course happens is all of that gas starts to attract all of the rest of it. This bit over here is attracting that bit over there. And so what will happen is the galaxy, or the nebula, will start to contract due to gravity as time goes on. But we said that this was rotating slowly. Look what happens when rotating slowly and I pull the contraction cord. So here, rotating slowly, I pull the contraction cord, and look how much faster it's going. Conserving something called angular momentum has meant that when the cloud of gas contracted, what happened was that its rotation rate sped up really, really fast. And so what started out as a very gentle rotation of the cloud became a whirlwind of motion to to what was forming after the nebula collapsed. So here is a photograph of a nebula. It's a giant cloud of gas and dust in space, bigger than a solar system. And this is the first step in the process of a star being born. You see, these regions collapse under their own gravity, and eventually enough gas and dust gets squished into an area for stars to form. But it's rotating, and that rotation is what causes the rotation of the solar system. But there's a step that we haven't spoken about. How do the planets form? We get that they're going to be rotating, but how do they actually form? Well, have a look at this. Check out this apparatus. I've got a bucket of water here, and there's a cork in the bottom of the water. And underneath, I've got a bucket to catch the water that's going to drain through when I pull the cork out.
I'm going to start the experiment by stirring the water with my ruler, and that's going to create a rotation. And when I pull the cork out, it will bend the surface of the water as it forms a vortex going down through the hole. But what it's going to do is it's going to create the same or very similar physics to the physics that determines what happens when the nebula collapses. What's going to happen is we're going to see rotation and we're going to see the formation of a solar system. So to start with, what you will see is the random scattering of dust all over, but then we should see it clump and form into little tiny planets. Now the only difference between this and reality is we then see it gets sucked down the plug hole, which doesn't happen in reality. It just orbits around indefinitely. So let's give it a go. And let's pull out the plug. And then we sprinkle on the powder. And there you can see what it's doing is we are seeing the formation of clumps, planets. Let's add some more powder. The formation of a protoplanetary disk. So that's what we believe happened. The nebula collapsed. The rotation rate increased. Most of the gas and the dust ended up at the centre and started to form a star. Up until the point when the star switches on and the light starts to emerge, we'd call it a protostar. And around that protostar is all of the material that was moving too fast to settle in the centre. All of that stuff carrying that rotation. A protoplanetary disk. Here you can see, just like in the bucket of water, the formation of all of that debris that's left over, moving too fast to fall in straight away, clumping up and forming little lumps within the disk, the planets as we see them today. Now eventually what would have happened is the presence of the strong sunlight at the point when the star switches on would have blown away most of the gas and dust that was here, leaving only the planets behind. And that leaves us with a solar system just like our own. So, you might be curious as to why the solar system formed into a disk in the first place. You may even have seen depictions of the atom where the nucleus is in the centre and electrons orbit in patterns kind of like this. But our solar system does not look like this. In fact, neither does the atom. But why doesn't it? Why does the solar system have a different design? The solar system has all of the planets rotating in a flat plane. Why was that? Well, it has to do with when that cloud collapsed and span up. What we think happened is this, that initially the sun was surrounded by a diffuse cloud on all sides. But the net rotation of this cloud was like this. It meant that some particles were going around like this, some asteroids or some rocks, but then there were other objects going around like this. In fact, at that stage, things were going around in all orientations. But because there was this net rotation of the solar system, then something started to happen. Objects that are going with the net rotation of the solar system met with less resistance than those objects going against it. It meant that objects going through this plane, like this object here, well, because this solar system was still thick with gas and dust, there's a kind of drag effect going on. But as it moved around here, what it would be doing is it would be swimming basically into essentially stationary gas, and that drag effect would start to slow down and act against its vertical motion. But any motion that it does have that is with the whole solar system, then it wouldn't feel any drag, because it would be moving with the gas and dust and rock around it. It meant that objects moving in the same orientation as the rotation of the solar system could continue to do so without any effects. But those objects that were going into orbits high above and down below the solar system were having their vertical motion, every single orbit, squashed and squashed and squashed through friction, until eventually all of the planets settled into orbits like this. Now those planets in a dusty solar system would have been spiralling towards the sun. The one thing they needed was for the sun to switch on. So a good question is to, why did the sun get so hot? So if gravity crunched down that gas into a small space, how did a star form? Well, with the compression of that gas came an increase in the temperature. We'll learn more about that later. What you can see here is I have a piston full of gas and a tiny bit of cotton wool at the bottom. And if I hit this piston hard enough at the top, I'll be able to get that cotton wool to get so hot it bursts into flames. Let's give it a go. The sun switching on blew away all of the remaining dust in the solar system. But why did the sun switch on? Well, nuclear fusion reactions, which we'll learn about in the radioactivity topic, began in the centre of the sun. A direct result of all of that pressure pushing down, increasing the temperature and causing it to get so hot. Now, the material of the sun is not like an ordinary fire. It is burning, but the energy is coming from a nuclear fusion reaction. That material, glowing red hot, is actually a different state of matter than what we experience in everyday life. It's not solid, liquid or gas. It is in fact a plasma. Now what I can do in this ridiculously foolhardy experiment that you are not to try at home is I can recreate a plasma similar to the sun. What I'm going to do is I'm going to light a fire inside this microwave. And when I do that, what's going to happen is that fire is not going to gain its energy from the chemicals released in the combustion, but instead is going to gain its energy from the microwaves. Now I must stress that this is foolhardy, but I'm a professional. What I'm going to do is I'm going to stick a lit match on this cork, and I'm going to place this Pyrex beaker over the top. Now these Pyrex beakers have an extremely high melting point, and so it will be able to contain 100, maybe 1,000 degree plasma inside of this. I'm going to put it in and I'm going to turn it on. I will, at all times, be wearing safety equipment, and we'll have things around to put out the fire that this is going to create. You may also find that this sets off smoke alarms. It's a very smoky experiment. But if you are ever thinking of doing anything like this, may I recommend this following thing? You need a kill switch. So look at the power cable on the floor, right? Just there, at a nice safe distance, is a place where I can pull the plug out of the socket without getting anywhere near the microwave. For once I set this thing off, I do not want to return to the microwave door to switch it off. Right, if we're all ready, then let us begin. Okay, so I'm going to light this. forming in the microwave. That is unbelievable. I'm going to have to hit the kill switch.
So when our sun switched on and nuclear fusion reactions took place, a huge amount of light was then sent into the solar system, blowing away all the dust. Oh dear me. Oh, I think we're going to need a new microwave. Stars, like our sun, can shine for billions of years. We call stars, at this point in their life cycle, main sequence stars. And they are there in a very stable way, with gravity pulling them down against the thermal pressure holding them up, and nothing seems to change. But then, conditions inside the star start to change. And I want to demonstrate this to you with these balloons. Behold the sun! And this is a representation of our sun in our solar system. It is just like all of those myriad of stars we see in the night sky. For 5 billion years, our sun has been stable. And for 5 billion years, we believe it will continue to do so. But what's going to start to happen when conditions become less favourable? When the nuclear fusion processes inside become strained by a lack of fuel? Well, our sun will swell up and become a red giant, just like what I have here. It will expand to the point where it swallows all of the inner planets. It's cooler and less dense outer atmosphere spreading into space. It's going to start leaking material into space. It's going to become a planetary nebula. And as it does, it'll give off all of the material into space that it was made out of, apart from a very, very small little core. And this is a white dwarf. All that's left over from our sun when it has died. It sits there in space, slowly cooling down until it is almost black. Now this is what happens if you're a small star. If you're a larger star, then something different happens for you. If you're a high mass star, then what happens when you become a red giant is this. You swell up, and you swell up until eventually one day, supernova. And what is cast through space is all of those small remnants that you were made out of, seeding space with gas and dust that forms into nebula and forms new stars. Now the most significant thing about this is the material that you are made from. That you, sitting there, are made from stardust, from an exploded supernova that occurred billions of years ago. So the life cycle of a star follows this regular pattern. All stars begin as a nebula, a cloud of gas in space. That, due to gravity, collapses and a proto-star is formed, around which a protoplanetary disk, out of which the planetary system forms. Then, when the star switches on and its nuclear fusion reactions begin, it is a normal star doing its normal thing. And for reasons that will become clear in a second, we call that a main sequence star. Our sun is at this stage in its life.
But then what happens next really depends on how massive that star is. You see, some stars are born with lots of mass as a result of them getting a larger share of the nebula to begin with. But some stars, like our Sun, get slightly less. We've had to share the material with other stars. And so we, as a low mass star, we follow an end of life route that looks like this. First of all, our star swells up to about the same size as the orbit of Earth, cools down, becoming red, and then eventually gives off all of the outer layers of the star into space. A gentle-ish process that we call forming a planetary nebula, which look like a ring in space. Now that ring is not wasted, because that ring of hydrogen and gas and dust is what will form further nebula to restart this process again at somewhere in the future. But what is left over of the core of the star, where the nuclear fusion reactions used to take place but don't anymore, well, that becomes the white dwarf that slowly sits there in space cooling down. Now, that's what happens if you're a small or a low mass star. But what happens if you're one of the big boys? If you are a high mass star, a different end of life sequence happens for you. First of all, you don't form just a regular red giant. Oh no! You form a supergiant. And these supergiants are truly massive, getting so large that they could engulf our entire solar system. This star is so large, in fact, that at one point a nuclear fusion process deep inside presses the detonate button and the entire star explodes in space, forming a supernova, casting nearly all of the contents of that star into the interstellar medium for it to form more nebula somewhere else in the galaxy. And that process is why all of the material in the stars is being recycled. And it is from that material that we are formed. But before we get carried away, let me show you that the final stage of what happens to the core of that star itself depends on mass. Stars of an intermediate mass, more massive than the low mass stars, but not the most massive in the universe, well, they become a special kind of star called a neutron star. And neutron stars are very, very small objects made out of, well, neutrons, crammed together with the same kind of density as the nucleus of an atom. That you could have a star almost as massive as our Sun, but packed into a space that is only about 15 to 20 kilometers across. Neutron stars were first detected because of their radio pulses by Jocelyn Bell Burnell at Jodrell Bank Telescope. And what she had discovered was spinning neutron stars, and they were called pulsars at the time. But there's one further thing that our Sun could do if it was really, really massive, and that is it could start to collapse in a way that there were no internal forces that could prevent that collapse. And eventually it would become so dense it would bend space and time to the point where light could not escape. And we call that a black hole. The black hole here is basically a huge hole in space where there is a strong gravity but no light escapes. Now, you may be curious how this was figured out. Well, it was figured out through this diagram. It is a Hertzsprung-Russell diagram. They were the names of the two scientists that figured all this out. It was actually originally called the Hertzsprung-Russell-Cannon diagram, but Annie Jump-Cammon was female, and as is with many of these great injustices of the time, her name was left off this diagram, so it's only named after the two men. Eisner Hertzsprung and Henry Russell. Anyway, that's not the point. This diagram helps us to understand what type of star these all are and where they are in their life sequence. You see, running through this diagram, on the axis we have got the luminosity with bright stars at the top and dim stars at the bottom. And then at the bottom we have temperature going from hot to cold. And you can see that means that the hot stars are blue, and then it goes white, which is a mixture of all colours, and then yellow, and then red. And what you can see is that most of the stars live in this band that runs through the middle. This is known as the main sequence. Now, all stars that are living the main part of their life exist somewhere on this band, on the main sequence. You can be a hot star, you can be a cold star, it doesn't matter. What we find is that the smaller mass stars are down here, the red dwarfs and things like that. And that our sun is about here, right in the middle, or just below the middle of the main sequence. But there are some bigger stars that go up here. Now, whether or not you are a bigger star or you are a star like our sun, what's going to happen is you're going to use up all your fuel and you're going to physically change. Now, what happens as our sun becomes a red giant is it doesn't particularly get much brighter, not a lot brighter, but most specifically it gets colder. And so what happens is the star leaves the main sequence and goes over here. And so what we find when we plot all of the stars that we can see on this sort of chart, that all of the red giants end up in the same place on the diagram. And these stars are the ones that when they die and give off a planetary nebula, the core of those stars ends up all the way down here. They are both dim and very hot, and hot objects tend to be white hot. So these are the white dwarfs down here. Because they are so dim and so small, they're very hard to see. White dwarfs. Now these ones up here are what happen when those high mass stars come to the end of their life. They leave the main sequence and they become the red supergiants. These ones are the ones that undergo a supernova. The neutron star and the black hole don't give out any light in the visible part of the spectrum, and so they're not on this diagram, they just fall off the bottom. But this Hertzsprung-Russell diagram, and this is how we write it, Hertzsprung and Russell, it is double L, diagram, helps us to understand where in the star's life that particular star is. It also enables us to predict what is going to happen to our sun based on where it is on this diagram right now. So that's it. That is stellar evolution. None of these details are superfluous. You need to be able to reproduce this diagram and understand the HR diagram and what it tells us in this level of detail.